I'm going to move then to my code, and we're going to solve a piecewise cubic spline using the linear algebra method that we've just developed. But then I'll introduce a SciPy library function that will allow us to, in general, solve the piecewise cubic spline interpolation of a set of data points. So the SciPy function that we will use for the cubic spline interpolation is this guy here. And when we use this, we will pass a pair of arrays, one containing the independent variables and one containing the dependent variables. So X and Y is in the prior example. So we pass those, and it's going to return to us a object that is the cubic function, is the cubic polynomial. The only other thing we pass that's important to pass to this has to do with that additional constraint that I mentioned, that there were different choices you could make about the very final constraint. Had to do with the bookend. So the choice that we made was that the curvatures at the far left and far right points, so the functions going through those points, was 0. So that's called kind of a natural, unbiased assumption. And so there's an argument where you can pick that assumption. But there are other ways to do splines. For example, you could imagine, well, I'm going to imagine that my 3 data points have a periodicity to them. So there's another set of 3 data points on the right, another set of 3 data points on the left. And so you could have a constraint that's based on that this function needs to be periodic. So that would be another way of doing a cubic spline. So that's this third argument here that says what type of spline. I've mentioned the natural one, I've mentioned the periodic one, and there are other ones too. Okay, so now I'm going to jump to my code for the cubic spline, and we'll just see how it works in terms of coding a cubic spline using linear algebra, and then how it works if we use the cubic spline function in the SciPy library. So here I'm just importing some of the packages that I need. I want to use some linear algebra packages, so I import that. I want to use some interpolation functions, so I import that. In this second cell here, I'm just defining a couple of things. One is the data points. And we're just working here with this simple case of 3 data points. And if you remember those data points, we had a independent variable X. The values of X are 0, 1, and 2, so equidistant data points. And the corresponding values of the dependent variable Y, those are 1, 3, and 2. So this defines my data that I want to interpolate. And then I define this large vector or a large array of finely spaced X points or independent variable points. This is going to be my proxy for not being able to have a continuous function in Python. I want to plot the function that I'm going to interpolate the data with. And so I'm going to use this array with finely spaced points as my kind of proxy for a continuous X value. And then from that, we'll generate the continuous proxy for the continuous Y value, which will be my interpolation. So that's just declaring that proxy for a function X. Okay, so the linear algebra problem that we're going to solve is the problem involving that matrix, we called it M, that define the constraints on the two cubic functions, a vector, I called it B, that contained the dependent variables, and we're going to take that matrix and that column vector B, and we're going to solve for A in the equation that A times the matrix M equals B. And so I've got to define B. So here's B, and this is just what I had on the slide. This is that column vector B on the slide. So this value 1 here is Y1. These 3s here are Y2s, and then this 2 here, that's Y3, and then these are all zeros. These zeros are because of the constraints that the curvatures were 0 at the ends, or the curvatures and the slopes were equal at that midpoint. So that's why those are zeros. And then here is the matrix. And this matrix I just copied from our derivation of this matrix from my slides. So I didn't really, I was thinking there must be a more rigorous way of doing this, but in the end I just copied it, or 64 numbers from the previous slide into this. Anyway, this is this matrix M that embodies these constraints on the 8 parameters of the 4 cubic splines. So we've defined M and we've defined B, and we want to solve for A, which is the values of the 4 coefficients of each of the two cubic functions. And so to solve for A, I'm just going to use this num-p linear algebra function. Actually, here's the linear algebra function that I'm using. That will solve for this column vector A. And so we're basically just taking the product of the inverse of the matrix M and B, and that will give us the vector A. And so we'll execute that. And then once I've got the coefficients, so A is a vector with 8 elements, and then the coefficients of it correspond to the coefficients of the 2 cubic functions. So here's the first cubic function. This is the cubic function that goes from the left-hand point to the center point. It has terms x cubed, x squared, x, and a constant. And their coefficients are the first four elements of this vector A. And then here's the second cubic function. Again, it's got an x cubed term, an x squared term, x term, and then a constant term. And the 4 coefficients of these terms are the last 4 coefficients in this vector A. And so S becomes, this is spline 1. This is the cubic function that's joining the left-hand point to the center point. This is S2 is spline 2. This is the cubic function that's joining the midpoint to the right-hand point. And moreover, these two cubic functions have been forced to have the same slope and the same curvature at the midpoint, and have been forced to have 0 curvature at the left-hand endpoint for S1, 0 curvature. So in these 3 lines, we're really solving the problem of finding the piecewise cubic spline that passes through these 3 data points. We're solving the linear algebra problem of finding the cubic functions from the 8 constraints on the cubic functions. And then I'm just going to plot them. So if you look at what I'm plotting here, I plot the data points, That's the xi's and the yi's. I plot the first cubic function, the one that I called spline 1 versus x. I plot the second cubic function, the one that I called spline 2 versus, and so here's our result. So firstly, magenta are the 3 data points. So that's what we're trying to interpolate between. The red curve is spline number 1, and it's the spline that we've arranged to go through the left-hand data point and the center data point. But it doesn't have to go through the right-hand data point. It's only interpolating between these 2 data points. So you see here, just heads off wildly into some other direction. The blue line, this is what we call spline number 2. It's the function that has to interpolate or pass through the right-hand data point and the center data point. So it does that. And again, in this region over here, it can walk wildly off. It doesn't have to go through the left-hand data point. It just goes through these 2 data points. At the center point, our constraints arrange that the slope and the slope and the curvature of these 2 cubics have to be the same here. And if you look, I mean, it's hard to see by eye, but they do look like they have the same slope. They do look like they have the same curvature. And then finally, we've arranged that if we were over here on the far left at this bookend, the curvature here, we constrain to be 0. And this line becomes kind of linear here by eye. And over here on the far right, we said at this bookend, the curvature is constrained to be 0. And you see this line becomes straight over here on the far right-hand side. So the 2 cubic functions seem to be obeying the constraints we applied in determining the coefficients or the parameters in those cubic functions. And so if you wanted to trace the interpolation, it's the line that is red over here on the left and then changes to blue over here on the right. That's the interpolating piecewise cubic spline. We can check that by calling this SciPy function that will do cubic splines for us. So that's what I do in this fourth cell here. I'm going to call the cubic spline function and obtain the piecewise cubic spline that goes through these 3 data points. So here's my call to that function. So here's cubic spline function in the library interpolate, which is in the package SciPy. The arguments, I mentioned them before, they're the data points. So here's the independent variable xi, here's the dependent variable yi, and here's that parameter that relates to your choices about how you're going to deal with the bookends on the far left and far right. We said we're going to make this so-called natural unbiased choice. We're going to make the curvatures 0 on the far left and far right. So that's what I'm doing with BC type. Boundary condition type is natural. Okay, so I call that function and it returns a polynomial object. We met polynomial objects in the last class when we were doing Lagrange interpolations, so that they're objects. You could print that object. It'll print out the polynomial itself. If you call that object with a single value as the argument, it'll tell you the value of the cubic function at that location. If you call it with an array, it gives you back an array of values for the values of the cubic function at all the elements of the array that you passed as the argument. And so that's what I'm doing here. My interpolating function or spline, I called it f. I called it with the argument x, which was our proxy for a variable x, and it returns the function y, interpolating function. So now I'm going to do the same plot as before, But in addition to plotting the data points, in addition to plotting the two cubic functions that together are the spline through the 3 data points, I'm also going to plot this this piecewise spline, which we defined as y. So that's this extra line here. And I'll plot that in green. And so that's what we get here. So the green curve, what's returned by CubicSpline, is the function that looks like the red curve over on the left-hand side of the center data point, looks like the blue curve on the right-hand side of the data point. So it is a single object that passes smoothly through these 3 data points.